Hello. In this video, we will discuss redox flow batteries. Specifically, we will explain the basics of how redox flow batteries work, their chemistries, applications, and recent developments. Before we can dive into redox flow batteries, it is important to understand the basics of how batteries work. A battery is a device that relies on electrochemistry and converts chemical energy into electrical energy, which we can use to power devices. In a battery, we have three main components: a negative electrode, which is known as the anode, a positive electrode, known as the cathode, and an electrolyte, which is a medium that can conduct ions between the two electrodes. In a battery, electrons flow from the anode to the cathode via an external wire, and ions flow through the electrolyte to allow for charge neutrality. There are several types of batteries with different chemical compositions, geometries, and arrangements, such as lithium-ion batteries, lead-acid batteries, and what we'll be talking about today, redox flow batteries. Redox flow batteries operate by the same principles as discussed earlier, however with some unique features. Redox flow batteries are composed of two half cells, where porous electrodes, an anode and a cathode, are separated by a selective ion exchange membrane. In terms of electrolyte, there are two types: an anolyte, which is a negative electrolyte, and a catholyte, which is a positive electrolyte. And these are stored in external tanks. These electrolyte solutions are then pumped from the tanks through their respective electrode, so the anolyte flows through the anode and the catholyte flows through the cathode. Because there's a membrane separating the electrodes, the catholyte and anolyte are never allowed to mix. Ions are then able to selectively cross this membrane, which prompts the flow of electrons and generates electricity.
Let's take a look at the chemical reactions happening at each electrode. Among many types of redox flow batteries, vanadium redox flow battery is one of the most prominent and well-established one. When the redox flow battery is being charged, the electron is provided to the negative electrode, reducing vanadium 3 plus cation to vanadium 2 plus cation. At the positive electrode, the vanadium monoxide 2 plus cation reacts with water to form a vanadium dioxide plus cation and releases a proton and an electron. This will cause the abundance of proton species near the positive electrode. Therefore, the proton ion migrates and diffuses from positive electrode to negative electrode. The overall charge reaction can be written as the following reaction. The discharge reaction of redox flow battery is the opposite direction of the charge reaction. Conventionally, the potential difference from the electrochemical reaction is compared with that of the standard hydrogen evolution reaction. The overall discharging reaction of the vanadium redox flow battery reveals 1.26 volts. However, this cell voltage is subject to changes in different concentrations of reactive chemical species, as Nernst's equation implies. However, redox flow batteries sometimes accompany competing reactions. The vanadium ions permeate through the membrane, since there is no such membrane that can block the crossover of redox species completely. The vanadium ions diffuse to the counter electrolyte, cause a cross-contamination reaction. Also, when the redox flow battery is being overcharged, some gases such as hydrogen and oxygen can evolve as a competing reaction. In addition, carbon dioxide gas can also be generated when graphite is used as a positive electrode. Therefore, the redox flow battery has to be handled with great care.
Now that we understand how the redox flow battery works, we will now look to see how RFBs fit into the greater context of energy storage devices. This table has competing technologies that are similar in application. The numbers are here for reference, but we'll just focus on the trends. Vanadium redox flow batteries have a relatively low amount of energy per volume and per density, which makes sense due to the large setup needed explained previously. The power, capacity fade, and efficiency are all relatively good, as well as the response time. And finally, it has a really long lifetime compared to other batteries, and is just as good, if not better, for how long it can discharge. There are some advantages and disadvantages that don't fit in this table, which are shown here. The total number of cycles does not significantly affect the performance of the battery, and the battery is relatively cheap when all the costs are considered over its entire lifetime. One of the biggest advantages of redox flow batteries is the very interesting feature of decoupled power and energy, which translates to the high degree of flexibility in design and scalability. In regards to the problems, its application space is limited by its low energy density, specific energy, and small temperature range for operation.
There are different applications to utilize the merits of redox flow batteries. The most promising field for redox flow system is stationary energy storage. First, load leveling is a method to balance the fluctuation between energy demand and supply. Redox flow batteries can store energy surplus and use the saved energy with lower cost than competitors. Uninterruptible power supply can be another product type that redox flow batteries can be used. UPS systems provide emergency power in case of the failure of the main power, and redox flow batteries can fulfill the requirement of stable energy supply and fast response time. Next, renewable power sources such as wind and solar devices show large fluctuation in their energy production. So to enhance the stability of these grid networks, redox flow batteries outperform over other types of batteries based on their cost, safety, system flexibility, and response time. Lastly, other than stationary usages, redox flow batteries are also expected to have increasing commercial space and large dimension electric vehicles in future.
Recent research has been focusing on reducing the cost and increasing the energy density of redox flow batteries. Organic redox flow batteries are a promising technology that use organic molecules such as DBIC instead of metals for energy storage. The advantages of organic molecules include they are cheaper and environmentally friendlier, and they exhibit tunability of both cell potential and solubility in the supporting electrolyte. The disadvantages are lower energy density due to lower solubility, and higher capacity fade due to chemical degradation. The key takeaways from the structural comparison are vanadium redox flow battery uses the same redox active material in both reservoirs and in an acidic medium. The big hexacyanoferrate redox flow battery operates in an alkaline medium. Vanadium redox flow battery employs a fluorinated membrane, while its big hexacyanoferrate counterpart uses a cheaper, safer hydrocarbon membrane. Here we look at 5 performance parameters. Energy density is dependent on cell voltage and electrolyte concentration. The cost of electrolytes and the calendar life of batteries provide a simple cost-value analysis framework. Vanadium redox flow battery has a lead over its big hexacyanoferrate counterpart in all categories apart from the most crucial one, cost. The images point to the decoupling of power and energy in redox flow batteries. As the generation of renewable energy grows daily, the necessity for energy storage solutions increases exponentially. Research efforts to reduce cost and increase energy density place redox flow batteries in a vantage position to be the safest, cost-effective solution, not only for stationary applications such as grid storage, but also for mobile applications such as powering electric ships. Thank you for watching our presentation.